in Jezero crater on Mars. Like every other element on the Mars 2020 spacecraft, individuals worked really hard and went above and beyond to make sure that their piece of the spacecraft did what it was supposed to do and would be successful. But in the end, we knew that our entry, descent, and landing camera system, the mission could still be 100% successful if our camera system didn't work. And if we could even get just one image or one piece of information back during EDL, that we shouldn't get upset and we should be excited. So as you probably realize after last Friday's press conference, the EDL cam system successfully captured some amazing imagery of the vehicle's descent and landing on the surface of Mars. We collected a little over 30 gigabytes of information and over 23,000 images of the vehicle descending down to the surface of Mars. As a quick introduction, if I could have the first graphic, a reminder for some of you exactly what are the sensors that we included in the entry, descent, and landing camera system. There are 3 cameras that are located on the top of the vehicle on the back shell. Those cameras actually capture high rate, 75 frames a second imagery of the parachute inflating in the Martian atmosphere. Now, one of the cameras stopped operating coincident with the mortar fire when the parachute was deployed, and that's to be expected. It is a very high dynamic environment, but luckily the other 2 cameras continued to operate as expected and captured some amazing footage of the parachutes inflating in that Martian atmosphere. We put one camera on the bottom of the descent stage. That camera looked down on the rover as we lowered the rover on the bridles. The mobility system latched into position, and then the vehicle touched down onto the surface of Mars. We also installed 2 cameras onto the rover, one on the top of the vehicle looking up on the descent stage so the rover could actually see the descent stage, lower it down to the surface, and then ideally fly off into the distance after it had delivered Perseverance safely onto the surface. And then we also put a camera on the bottom of the rover, which actually looked down on the surface of Mars once the heat shield was dropped away, and that camera continued to capture imagery until the vehicle touched down on the surface of Mars. And then we also put a microphone on the port side of the rover. Now, unfortunately, I do have to say that we did not collect any audio during EDL, but please stay tuned a little bit later in this press conference because we do have some exciting information about the EDL cam microphone. So now the reaction to the EDL cam videos has been absolutely amazing around JPL. And we are super excited to actually share with all of you video imagery of Perseverance landing on the surface of Mars. Please roll the video.
Starting the straighten up and fly right maneuver, where the spacecraft will jettison the entry balance masses in preparation for parachute deploy and to roll over to give the radar a better look at the ground.
Applicant indicates chute deploy.
The navigation has confirmed that the parachute has deployed, and we are seeing significant deceleration in the velocity. Our current velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars.
Heat shield set.
Perseverance is now slowed to subsonic speeds, and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
Nav filter converge. Velocity solution 3.3 meters per second. Altitude 7.4 kilometers.
Now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers above the surface of Mars. Perseverance is continuing to descend on the parachute. We are coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
LVS valid.
We have confirmation that the lander vision system has produced a valid solution and part of terrain relative navigation.
Timing. TBA is nominal.
We have timing of the landing engines.
Back shell set.
Current velocity is 83 meters per second at about 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about a kilometer off the surface of Mars.
TRN Safety Bravo.
We have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars. We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver. Sky crane maneuver has started, about 20 meters off the surface.
We're getting signals from MRO. Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the sands of past life.
It gives me goosebumps every time I see it. Just amazing. I hope everybody kept their hands and arms inside the vehicle at all times while it was in motion. So I do need to say I wouldn't be sitting at this podium, and you wouldn't have all seen that amazing imagery without a lot of support from an amazing team, both those who worked directly on the EDOCAM task as well as those who supported us across the project. I thank you for everything you've done to get us here today. Just an amazing, amazing accomplishment. So I'm going to turn it over to Al. Al is going to be our color analyst. He doesn't have a telestrator, but he's going to actually walk through some of those videos in even more detail and actually show you some just incredible things that you can actually see once you look at those videos over and over.
I'm not sure the color commentator is supposed to have as many chills as I do right now and every time I see these videos. But I wanted to add my thanks to the EDL camera team. I mean, these videos and these images are the stuff of our dreams. It's been what we've been dreaming about for years. So thank you so much. Let's see. As Dave mentioned, we'll try to walk through what we see a little bit. We won't take that much time because we could spend literally all day looking at these videos, and some of us have spent all the weekend looking at these videos. But we'll just try to show you some highlights of what we've been seeing and invite you all to continue to look for more things as we kind of see new things every time we look at these videos. So let's start with the parachute uplook camera, and let me give you a quick warning to not blink because things go really fast here. You can see that you can get a sense really of how violent that parachute deploy and inflation are. The parachute is packed so densely that the pack is basically the same density as oak, and it's about 150 pounds. It gets launched out of the spacecraft with a mortar, which is basically a cannon, with a muzzle velocity of around 100 miles an hour. And the spacecraft itself was going about 1,000 miles an hour at this point, going about 1.75 times the speed of sound. So just in case you blink, let's show you that one more time. You can kind of see that in high speed and then or real time, and then we'll slow it down and take a look at the details. Okay, so let's try to walk through this a bit slower, this time at about quarter speed, and we'll pause at times to point out things we see. So let's start that rolling. Okay, here you can see the pack getting pushed out of there. You can kind of see the pack right in the middle as it's being pushed, and the parachute lid, which is right on top of it, it's kind of that circle to the left of the pack, was on top of the pack. And it was there to protect the parachute during entry. It's got some thermal protection system material on it to keep the parachute nice and cool and protected. And the pack is used to push that lid right off the vehicle, given that cannon force. You can also see some of the other things that have popped off of that lid, which is kind of expected given how violent this launch really is. So let's move on from here. So we keep going out here. You can see the pack reach what we call line stretch. So that's as far as it's going to go. It's where the parachute's going to start inflating. That's about 150 feet behind the spacecraft, and it got there in just under 1 second. So this pack is really moving. That's pretty much, as the parachute starts to come out, you can see the pack is rotated about 90 degrees. That's pretty common. We've seen that in some of our testing here on Earth at high altitude as well. So let's keep going and take a look at the inflation. So that inflation really looks textbook. It's nice and symmetric. The parachute opens in only about 7/10 of a second, again, really fast. There's no evidence of tangling of the lines, which is great. There's about 2 miles of lines in the parachute system, so the fact that we don't see any evidence of tangling or any kind of other misbehavior is great news. And I'm sure we'll be studying this video for many, many years and picking it apart frame by frame. And of course, we have a second camera on board as well that recorded this launch and inflation of the parachute. You might notice the pattern that's on the parachute here. Distinct patterns are useful in helping us determine the clocking or orientation of the parachute. Also, the contrasting sections can be useful in tracking different positions of the parachute, different portions of the parachute as it inflates. So it's especially useful when we have multiple cameras, as we do here, and are trying to track features in the parachute inflating. In addition to enabling incredible science, we hope our efforts and our engineering can inspire others. Sometimes we leave messages in our work for others to find for that purpose. So we invite you all to give it a shot and show your work. Let's move on to the rover downlook camera and take a look at that in a little bit more detail. So if we start that up, you can see the heat shield falling away very nicely and symmetrically. Pausing here, we can take a look at what we see on the heat shield. First, we see the medley components on the heat shield. You can see the electronics box and the gold wires that lead to all the various sensors that measure the aerodynamics and heating during the entry portion of flight. We can also see some white flecks in different places, both on the heat shield and free flying, which are likely frost that accumulated on the heat shield. That heat shield is really, really cold during cruise, so it's not at all unexpected to see some of that frost appearing on the heat shield on the inside. You can also see something we didn't expect to see if you kind of look at the 4 o'clock position on the heat shield or so, towards the middle, somewhere between the middle and the edge. One of the springs that helped push the heat shield off seems to have come loose. It's not much of a big deal, but it's definitely not what we expected. If you look at the other 8 springs, they actually are where they're supposed to be, all around the edge of the heat shield. There's no danger to the spacecraft here, but it's something we didn't expect and something we wouldn't have seen if we didn't have the camera system to show us what was going on. So let's keep rolling here. We can see that the heat shield basically stays in the same orientation as it flies away from us. It'll come back into view in a little bit. But this is great. This is kind of what we expected in terms of the aerodynamics of that heat shield. It doesn't tumble or do something weird that was unexpected in flight. So that's very useful to have this video to show us that. So in the interest of time, let's skip ahead to